We're going to talk about sequences in this lesson. A sequence is simply a list of numbers. It's a list of numbers, and usually there is some type of pattern to get from one number to the next. So we can list out numbers with commas separating each term, and sometimes they'll have a comma dot dot dot, meaning that that sequence goes on forever. Otherwise, without that, you have just a sequence of a specific number, a finite number of terms. The example on the right, sometimes they use parentheses, and they say this is our sequence of numbers, and then they'll use a comma dot dot dot, and this sequence goes on infinitely because of the dot dot dot. In both cases, we can look at the patterns that occur, and we can try and come up with some type of formula that will allow us to find any term in the sequence. So I'm going to just make this finite sequence infinite by putting that dot 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 at the end. And let's look at what's happening. So when I look at the pattern going from 1 to 4, and then 4 to 7, and then 7 to 10, I'm looking at what we do to the previous term to get the next term. And in this case, we are adding 3, which is a constant pattern. It doesn't change. You continue to add 3 to the previous term. Now, a sub n represents the value, this is the value of the nth term. A sub 1, let me use a different color here. A sub 1, I'll just use gray. A sub 1 is the value of the first term. A sub 2 is the value of the second term. A sub 3 is the value of the third term. A sub 4 is the value of the fourth term. And then somewhere down the line, we might have a sub n. And that's the value of the nth term. So we want to write some kind of formula that allows us to find the value of the nth term without having to find every term in between. So we're just going to kind of think about this intuitively. If I want to get the first term, what would I need to do? Well, the first term, let's think about this. Our first term is 1, our second term is 4, our third term is 3, and our fourth term is 10. Let's think of this in terms of maybe the second term. So if I were to put if I were to put 2 in for n, what would I have to multiply by? So if I put an n in, so I can be talking about any term right here. So if I put, let me just make my marker darker. What would I have to either multiply or add to n to get that value? So we're just thinking intuitively. Well, if we're talking about the second term, just because I like to use that 4, I'd have to multiply it by something and then add maybe some kind of other value. So let's just say, what could we do? We could say 1 times n. I could say 1 times n plus 3. Okay, that would actually give me 5. So you're probably going, where are you getting 5 from? If I'm looking for the value of the second term, I'd put a 2 in for n, a sub n. That means that n equals 2. So the second term, 1 times 2 is 2, 2 plus 2 is 4. But does that work for the third term? So if I put a 3 in, 1 times 3 is 3, 3 plus 2 is 5. Yeah, so that does not work. But we're going to practice here. Let's try putting in, let's say instead of multiplying by 1, let's multiply by 2. So I'll multiply by 2. And now I'll put that 2 in. 2 times 2 is 4, and I don't need to add anything. That's pretty cool. Let's try a 3. 2 times 3 is 6. That doesn't give me 7. 2 times, and I need a 7 for the third term. Okay. maybe I have to subtract values, or maybe this 3 plays a role. So let's look. Let's put a 3 right here and see what we have to do there, because we keep changing this coefficient of n. So the value of the first term, let's say a sub 1, I put a 1 in for n. 3 times 1 is 3, and then to get down to 1 I'd have to subtract 2. Okay, that works, right? Now let's try it for 2. So you put a 2 in. The value of the second term, 3 times 2 is 6. 6 minus 2 is 4. That checks out, so those two check out. Let's try 3. 3 times 3 is 9. 9 minus 2 is 7. And that is the value of the third term. So I think that we've got, I'm just going to try one more. Let's try a sub 4. If I put a 4 in for n, 3 times 4 is 12. 12 minus 2 is 10. And that is our rule. So I'm going to erase all of this. And I'm going to show a little bit more work here. So a sub 1 is equal to 3 times 1 minus 2. A sub 2 is 3 times 2 minus 2. A sub 3 is equal to 3 times 4 minus 2. Is that right? 3 times 2 minus 2. 3 times 2 minus 2. And then a sub 4 is 3 times 2. Sorry, messed that up. 3 times 3, 3 times 4 minus 2. Okay, so let me show you where those values were coming from. So a sub 1, n is 1. A sub 2, n is 2. Let me write this nice and thick here so that you can see it. A sub n equals 3n minus 2. So everywhere you see an n, we're putting in the number term. So the third term, we put a 3 in for n. The fourth term, we put a 4 in for n. That looks like it is indeed our formula. So it can be tricky. It can be tricky when you're not dealing with any rules. So hopefully you'll say, you know what, I'm going to welcome the rules when I can find them. Let's try. Okay, let's look here. How do we get from 3 to 7? What's the pattern? 3, 7, 11, 15. Well, this is another one where we're just adding 4, adding 4, adding 4, and that would be our pattern. So remember, right here, this 3, I'm going to change this colored highlighter and use a highlighter. This 3 right here, we eventually got right there. So let's try that with the 4. So let's see what's happening here. So we've got 4 times n, and we're looking for the value of the nth term. So when I put in a 1, let's see, 4 times 1 is 4. I need to get a 3, so I'd have to subtract 1. Okay, let's try the second term and see if this works. 4 times 2, because again, we're putting in for n a 2. And then the rule is subtract 1. So multiply 4 times n and then subtract 1. And that is 7. So far this is working. A sub 3 is going to equal 4 times 3 minus 1. 12 minus 1 is 11, and yep, that worked. And then a sub 4, that's the value of the fourth term. 4 times 4 minus 1, which is 15. And that one worked as well. So that is our formula. Not that, minus 1. That is our formula for the second example. These can get a little tricky when we start dealing with different types of formulas, or different types of sequences, which relates to different types of formulas. So let's just look at something. Let's look at, let's look at 1, and then maybe 4, then maybe 9, and then maybe 16. So I'm going to repeat that. 1, and then 4, and then 9, and then 16. And do you know what number would come next? If you know 25 comes next, then you know this formula. So this was the first term. The first term is 1 squared. The next term is the second term, and the second term is 2 squared. Then we have the third term, and that's 3 squared. Then we have the fourth term, which is 4 squared. The fifth term, which is 5 squared. So if I said n, the nth term would be n squared. So the value of the nth term is equal to n squared. This is why it is a really, really good idea to know 1 squared through 25 squared. So those are new math facts that you should have at this college level. 1 cubed through 10 cubed. So that would be 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, 6 cubed, 7 cubed, 8 cubed, 9 cubed, 10 cubed. You should be able to know these within about 2 minutes or less. 2 minutes or less. 1 to the 4th to 5 to the 4th, and 1 to the 5th through 4 to the 5th. So that's not a minus sign, that's through. So you should be able to do 1 squared, 2 squared, 3 squared, 4 squared, and be able to recognize those numbers. And this is why it's so important to be able to recognize those numbers, because I can take this sequence and I can tweak it just a tiny bit. I can take it and I can say 0, 3, 8, 15, 24, and so on. And when you recognize those numbers are being just 1 off from your n squared, you know that you've got n squared minus 1. So you're going to take 1 squared and then subtract 1. 2 squared, subtract 1. 3 squared, subtract 1. 4 squared, subtract 1. So these numbers start looking very familiar. However, if you do not know your squareds, your cubes, your fourth powers, some of these sequences will be quite challenging to figure out. Some of them will be quite challenging to figure out. So that's a good example of that formula, and then a sub n is equal to n squared. That's a great formula. Now this is all to be able to find the nth term. Sometimes we just want to find the next term. So how do we find the next term? These are called, I'm going to come back here real quick, and I want to just write this down. These formulas are called explicit formulas. So this is the explicit formula. This allows one to find any term, any term's value, without having to know the one before, the term before. I'm going to say the previous term. The previous term. Okay? And all of these are explicit formulas. So I'm going to highlight these all in that blue. That's an explicit formula. Explicit formula. This right here is an explicit formula. This is an explicit formula. All of those are an explicit formula because I can find any term. Meaning, if I wanted to find a sub 7, so I want to find the 7th term, I would just have to take 7, square it, subtract 1. If I want to find the 21st term, I don't have to expand this all the way out and find the 20th term and then figure out what the 21st term is. I can go right to this explicit formula and I can say 21 squared minus 1. and 21 squared is 441, minus 1 is 440. Do you see how knowing that math fact makes me come across like I am really good at math? Which I'm good at arithmetic because I have some facts down, but there's other things about arithmetic that I'm not all that sharp with. But it definitely gives me confidence when I can take 21 and square it very quickly and I don't have to pick up a calculator. So those are some math facts that would be very, very helpful for you to have. Okay, let's talk about the recursive formula. This one's really important, the recursive formula. The recursive formula, so I already defined the explicit. The recursive formula allows you to find the value of the nth term in terms of the previous term. So the recursive formula is written for a sub n in terms of a sub n minus 1. And a sub n minus 1 is the value of the term before a sub n. So if n is 8, n minus 1 is 7. So if I'm looking for the value of the 8th term, if I'm looking for a sub 8, I'm going to need to know a sub 7. And then of course you're going to do something to that previous term, maybe add 3 to it, maybe multiply it by 2, maybe multiply it by a negative. Didn't want to erase all that. I just wanted to erase this, delete that, and let's take a look. So let's use the sequences that we already were exposed to, and then we can compare. So the first one was 1, 4, 7, 10? It was 1, 4, 7, 10, ... And remember that we added 3 to get from one term to the next. So what do you do to get the next term? You add 3 to the previous term. Add 3 to the previous term. So the value of the nth term is equal to, I'm going to write that in black. The value of the nth term is equal to the value of the term before it, and then I'm going to use red. The value of the term before it plus 3. Plus 3. So and if you can write this down, if you know the language and what this means, the value of the nth term equals the value of its previous term, that's what n minus 1 in that subnotation, value of its previous term, and then plus 3. And that's called the recursive. This is called the recursive formula. The recursive formula is definitely much easier to use. It's easier to define and come up with. However, it's not always the nicest when you have to find just one term that's way deep in the sequence. So let me show you another one, 3, 7, 11, 15. Okay. So what do we do to the previous term? Well, the previous term, we add 4. So we're adding 4 to the previous term, so that would be the recursive formula for that example. Let's look at a new example of numbers. 3, 6, 12, 24. What are we doing here? How do we get from one number to the next? Well, in this case I add 3, but then I'm adding 6, and then I'm adding 12, and that is not the same thing. So what am I doing to each term? What's the pattern? Well, the pattern here is multiply by 2. So multiply by 2, 3 times 2 is 6. multiply by 2, 6 times 2 is 12, multiply by 2, 12 times 2 is 24. So to find the nth term, I would need to take the previous term and multiply it by 2. So I'm going to rewrite that. A sub n equals, and I'm going to put that 2 out front, this way I don't have to use that funny looking multiplication symbol, 2 times the previous term, a sub n. And this is going to be true when a sub 1 is equal to 3. So we have to really now think about that initial condition, because how do we get to the second term for this one up here? Well, we have an initial condition that first term is equal to 1. And what was our initial condition here? Our initial condition here is the first term was equal to 3. So that's our recursive formula. Now we could write an explicit formula, and let's do that. How would we write an explicit formula? What if I don't want to find every term in the sequence to get to the 8th term? I don't want to find the first 7 terms to get to the 8th term. I just want to go straight to that 8th term. Well, the value of the nth term, now we're going to have to think about this. The value of the first term is 3. The value of the second term is 6. So what is our pattern here? 3, 6, 12, 24. It looks like that multiply 2. Look at this. So this right here, it's really cool. This right here, we're multiplying by nothing. That's our first term. What are we multiplying in our second term? Well, I started with 3. How do I get from 3 to 6? I multiplied by 2 once, right? And then we started, let's see, we started with 3. And then how do I get to the third term? Well, the third term is 12. How do I get to 12? Well, 3 times 4, so I multiplied by 2 twice. That's kind of cool. Okay, let's do the fourth term. Okay, I started with 3, and then I multiplied by, what do I need to get to? 24. 3 times 8 is 24, and there's that 1 cubed through 10 cubed. 8 is 2 cubed. So what's the relationship here? Well, if I wanted to find the second term, I needed to multiply my first term times 2 once. If I wanted to find the third term, I multiply my first term by 2 twice. If I want to find the fourth term, I multiply by 2 3 times. So if I want to find the nth term, I'm going to multiply by 2 n minus 1 times. A sub n is equal to the first term times 2, but I have to multiply by 2 one less time than the numbered term, okay? One less time than the numbered term. See, one less. 1 is 1 less than 2. 2 is 1 less than 3. 4 to 3, that would be 3 is 1 less than 4. So therefore n minus 1, 1 less than n. Now these can be very tricky. These can be very, very tricky to solve. So you had that written down and I already used that. So you're going to do your best to try and find the formula, and then we're going to work in the future with some specific types of sequences that it is much easier to use. So be patient with yourself as you try and find these patterns and put them into a formula. Don't be too hard on yourself. Okay, here we have if a sub n is equal to n squared minus 10 over n plus 1. This is an explicit formula. So this is explicit because it's not defined in terms of the previous term. This is an explicit formula. We want to find a sub 4, plus a sub 9. A sub 4 plus a sub 9. So first I'm going to find a sub 4, and I'm going to use my formula, that given formula. So we'll take a sub 4, we're going to put it right there. A sub 4 is equal to, I'm going to go to the formula, everywhere I see an n, I'm going to put a 4 in its place, 4 squared minus 10 over 4 plus 1. 4 squared is 16, 16 minus 10 is 6, 4 plus 1 is 5, a sub 4 is 6/5. Now I'm going to find a sub 9. So a sub 9 is equal to, I'm going to go back to this formula, 9 squared minus 10 over 9 plus 1. 81 minus 10 is 71 over 10. Now I'm going to take 6/5 and I'm going to add 71/10 to it. I'll get a common denominator. So I've got 12 plus 71 all over my common denominator of 10, which is 83 over 10. That does not reduce. That is my answer, 83 over 10. So that's one way that we can use our formulas to maybe find the sum of two numbers. That's a type of problem that you might find. Sometimes we need to find the sum of the sequence. So sometimes I want to know the sum of a sequence. This is where we use, or you might see, sigma notation. Okay, so sigma notation, it's a Greek letter, sigma, and it means summation. And then you're going to have your rule. So this right here is your rule, your explicit rule. And we've got k here. I'm gonna change it to n just so that we're using the same letters. Okay, we'll change it to n, but you could use any letter, k, a, x. You can use any letter you want, but I'm going to stay consistent and use n. And then this is your starting integer right here. So this is the first integer that we substitute in. And then this is our last integer that we substitute in. And we substitute every integer in between. So now I'm going to expand this. So what this equals, so now I'm going to expand. We call it the expansion. So this is the expansion of your sigma. I'm going to put a 3 in for n. So I'm going to have 3 squared minus 5. Plus, now I'm going to put a 4 in for n. 4 squared minus 5. That's my second term that I'm going to be adding in this sum. And then the next value I'm putting in is a 5, 5 squared minus 5. And then we put in 6 squared minus 5. And then we put in 7 squared minus 5. Now, 1, 2, 3, 4, 5 values that we're going to be adding together. So 5 values. How do we get 5 values from 7 and 3? Well, 7 minus 3 is 4. 7 minus 3 is 4, and then add 1 back. So 4 plus 1 is 5 values that we'll be adding together. The first value is 4. The second value, 16 minus 5, is 11. The next value, 25 minus 5, is 20. The next value, 36 minus 5, is 31. And then the next one is 49 minus 5, which is 44. Let me make sure that I did not mess up on my addition, subtraction, multiplication. We're good. So I add usually in groups. This is 75. And then I have 15 plus 20 is 35. 35 plus 75 is 110. And that is what, that's a funky looking sigma. Let me fix it. That's what this value is equal to. It's equal to 110. And that's the expansion. That's how you expand out your sigma. So let me do a couple more problems with that. And if you can get used to sigma and what you're supposed to do and what all the parts mean, then you can go backwards and you can come up with the rule and rewrite a sum in sigma notation. So here we have from I equals 3 to 6. I is just a variable. It is not imaginary. So I is common. It's not imaginary. Not imaginary. And it is common when using sigma notation. Okay. Usually the first thing I do is I figure out how many terms I'm going to be adding together. So maybe count how many terms. That would be step 1. How many terms will I have? How many terms? So I'm going to have 6 minus 3 plus 1. Remember, this is where it's coming from. 6 minus 3. And then you always add back 1. So that's going to be 4 terms. So 4 terms I'm going to have. 4 terms. And now I'm going to expand. So let's expand. So that's our second step. When I expand, I know that I'm going to have 4 terms. I know not to go too far. If I go too far, then I've made a mistake. So that's I equals 3 to 6. I plus 1 over I minus 1. I'm going to put a 3 in. 3 plus 1 over 3 minus 1. Plus, now I put a 4 in. 4 plus 1 over 4 minus 1. Plus, so there's my first term, my second term. Now I'm on 5. 5 plus 1 over 5 minus 1. I'm just putting in these values in for I. And then my last is going to be that 6. 6 plus 1 over 6 minus 1. So I have 4 over 2 plus 5 over 3 plus 6 over 4 plus 7 over 5. And now I get to add all of these together. This is 2 plus 5 thirds plus 3 halves plus 7 fifths. When I add fractions, I have to have a common denominator. So I'm going to add these 3 fractions. The first fraction needs a 2 and a 5, so that's 10. The second fraction needs a 3 and a 5, so that's 15. The third fraction needs a 3 and a 2, so that's 6. And that common denominator is 30. So I have 50 plus 45 plus 42 over 30. And then I'm going to have plus 60 over 30. 60 plus 50 is 110. 45 plus 42 is 87. That's 197 over 30. And that's what the sum from I equals 3 to I equals 6 of I plus 1 over I minus 1 is equal to. Okay, here's one for you to try. I'm going to use k. K equals 1 to 6, and our rule is 2 to the k power. See if you can expand that out and then get your sum. And when you're ready to reveal the answer, come on back and I will reveal the answer. Okay, welcome back. 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, and 2 to the sixth. We have 6 terms that we're adding together. 2 plus 4 plus 8. Now you should know these, or at least be able to figure these out. 16, and then 32, and then 64. You notice that we are multiplying by 2 to get from one term to the next. We have an exponential base happening with a variable exponent. We're going to talk about that in future lessons. 2 plus 4 plus 8. Well, that's 14, and 14 and 16, that's 30. That's the extent that I'm going to do there. And then I've got 96, so that's 126. So if you got 126, you've got it. Now there's 10 problems in the assignment that goes along with this lesson. It will challenge you, but that challenge is going to help grow your knowledge when it comes to sequences, so then we'll be able to put this together with arithmetic sequences and geometric sequences.